In this example, we're going to write an overall reaction for the process represented in a mechanism shown here that represents the oxidation of bromide ion in an acidic solution that contains some hydrogen peroxide. We're next going to identify intermediates in this reaction, write a rate law for the reaction, and sketch a reaction diagram. To begin, we've got 3 elementary steps for this reaction. In the first step, which is fast, hydrogen cations react with hydrogen peroxide to establish an equilibrium with some activated complex, H3O2 cations. The forward reaction is represented by rate constant K1. The reverse process of exchange back to the original reactants is represented by rate constant K minus 1. In the second elementary step, which is slow, this product, H3O2 plus, reacts with bromide ion in solution to form HOBr and H2O. This process in one direction is represented by the rate constant K2. In elementary step number 3, which is fast, HOBr goes on to react with excess hydrogen cations and bromide anions to form molecular bromine and H2O. This is a single-step reaction represented by K3. Overall, our net reaction is given as the sum of each of these elementary steps. We can get rid of things that are the same on either side of a reaction arrow, like H3O2 plus in the first step and the second step, and HOBr in the second and the third step. Everything else is additive. We have 2 H pluses on the left-hand side of our net reaction, 2 bromides, and H2O2. On the right-hand side of our reaction, we have 2 water molecules and molecular bromine. Here's our overall reaction that represents these mechanistic steps. The substances H3O2 plus and HOBr were produced in elementary steps of this reaction mechanism and later consumed or used up in subsequent steps. Those represent, therefore, intermediates in this overall reaction. We say that the complex H3O2 plus and the molecule HOBr represent intermediates in the overall reaction. To write a rate law for this reaction, we'll take advantage of what we know about the reaction mechanism. From our mechanism, we know that step 2 is a slow step. The slowest step in a reaction mechanism is always the rate determining step. It determines the overall speed of our reaction. We can write down a rate law directly from the second elementary step in our mechanism. That looks like this. Our rate of reaction is equal to our rate constant for that step, K2, multiplied by the concentrations of either reactant raised to their stoichiometric coefficients, which are both 1. So our rate of reaction looks like this. K2, the rate constant from step number 2, multiplied by the concentration of H3O2 plus cation, multiplied by the concentration of bromide anion, which is all well and good, except that this substance, H3O2 plus, we've already identified as an intermediate in the reaction. It doesn't show up in our overall net reaction, and therefore there's no way for us to track it directly. We're going to have to find some means by which to substitute an expression for H3O2 plus. To substitute an expression for H3O2 plus, we look to the other elementary step of our reaction mechanism to identify another case where we see it in the first place. We see H3O2 plus in elementary step number 1. It's produced through the forward reaction, and it's consumed through the reversed step in that reaction. In other words, the forward reaction that produces H3O2 plus has some rate that's given as K1, the rate constant for the forward reaction, multiplied by the concentration of H plus cation and by the concentration of hydrogen peroxide. The reverse direction that consumes that product has a rate that's governed by K minus 1, the rate constant for the reverse, multiplied by the concentration of H3O2 plus. At equilibrium, what we'll find is that the rate of the forward reaction is equal to the rate of the reverse reaction. We establish a balance between the two. In other words, K1 times the concentration of H plus times the concentration of hydrogen peroxide is equal to K minus 1 times the concentration of H3O2 plus. We can rearrange this expression and solve for H3O2 plus concentration in terms of other things that we do know about. That's K1 times H plus times H2O2, all divided by K minus 1. And this expression allows us to substitute in anywhere we see H3O2 plus, like in the rate law we drew above. So let's substitute that expression in. In our rate law, we had K2 originally, multiplied by H3O2 plus concentration, which we're now going to use this to represent. K1 times the concentration of H plus times the concentration of H2O2, all divided by K minus 1, multiplied by concentration of bromide. To clean this up and make it look a little nicer, we can say that the rate for this reaction is K2 times K1 over K minus 1 multiplied by the concentration of H plus multiplied by the concentration of H2O2 multiplied by the concentration of bromide. An even more succinct way to put this is to represent this whole expression of individual rate constants from individual elementary steps as a cumulative rate constant for the overall reaction, K. And in so doing, say that the rate is equal to K times the concentration of H plus times the concentration of H2O2 times the concentration of bromide. Here's our rate law for the reaction. Finally, to sketch out a reaction progress diagram, I've set up a set of axes on the right-hand side where we have energy as a function of reaction progress, or how far along in a reaction we've gone. Our reaction diagram should be represented by 3 peaks that represent each of our 3 individual elementary steps. In step number 1, we have to overcome some energy barrier in order to produce H3O2+. That's a fast process, though, so there must not be too high an energy barrier. In step 2, which is a slow process, however, the energy barrier must be comparatively quite high in order to produce our products, HOBr and H2O. Finally, our third elementary step is, again, fast, meaning that the energy barrier to that process must be low compared to the second elementary step. Sketching this out, we might draw something that represents hills that are large for slow processes and comparatively smaller for fast processes. In this reaction diagram, the first hill represents elementary step number 1. The second hill represents elementary step number 2. And this final hill represents elementary step number 3. Overall, the largest hill to climb represents the largest barrier to the reaction moving forward, and so determines the overall rate of our reaction.